Okay, good evening. This is Professor David J. De Los Reyes. Okay, the date for today is of November 7, 2023, and the time is around 10:37 p.m. Okay, my topic for tonight will be a continuation of my long video format subject matter on trigonometry, and we are now on lesson number 19. Lesson number 19. Okay, and the title of the topic is actually, this is in relations to logarithms, so it will be solutions of problems involving logarithmic equations. Okay, let's proceed. The subject matter for tonight will be a long video format. This is a subject matter on trigonometry, and we are now on lesson number 19. So for those of you who are following my long video format topic trigonometry, we are now on lesson number 19, and the title of the topic is logarithmic equations. This is still in connection with the so-called study of logarithms. One of the problems that are coming out on YouTube are actually logarithmic equations. So before we will take another topic, maybe obtuse angles on trigonometry, let's try to finish first this topic on logarithmic equations, meaning an example problems and how to solve logarithmic equations. Okay, I will give you example number one. We are given example number one. We are given the logarithmic equation. Okay, the common logarithm of x plus the common logarithm of the ratio x over 4, and they should be equal to 4. The problem is asking what will be the value of x. Okay, let's try to bring out the solution. The given equation is actually a logarithmic equation. It's a common logarithm because the base is not given. If we are given a log sign without the base indicated, it is understood that this is common logarithm, meaning the base here is actually equal to 10. But under the study of logarithm, if the base is not given, it is understood that the base is 10, or we shall erase it. It is understood that the base of this one is actually 10. Okay, let's try to bring out the solution. I will rewrite this one. It should be logarithm of x plus the logarithm of this ratio. I will now be using the logarithm of equation. The logarithm of equation is actually the logarithm of the numerator minus the logarithm of the denominator. So log of x plus log of x, the logarithm of the numerator, the denominator is 4. This is under 1 logarithm sign, so this is minus the logarithm of 4, and this should be equal to 4. Combining similar terms, this is 1 log of x plus 1 log of x, that will be twice log of x, and this should be equal to. We transpose the constant term on the left going to the right, so we could isolate the x from the pure constants. So this should now be equal to 4 plus the logarithm of 4, that is, this is after the transposition, right? So twice the logarithm of x should be equal to 4 plus the logarithm of 4 with the base of 10 by using our calculator. It will be 0.602. So twice log of x will be 4.602. Solving for logarithm of x, we divide both sides of the equation by 2, or just simply multiply this by 1/2. This one cancels. Log of x should be equal to 4.602 times 1/2, or that will be 4.602 over 2. Log of x will be 2.301. So this is now the final equation, okay, after the simplification, but that's not the value of x. We must have to solve the value of x without the logarithm sign. And to eliminate this logarithm sign, we must have to take the antilog of both sides. And the proper way on how to take the antilog of both sides is take the base, raise that left hand side with that base, and so with the right hand side. The base is actually 10, so this should be 10 raised to the logarithm of x, meaning we are taking the antilog, equal to 10 raised to 2.301. But this one here is just simply x. Okay? So x now, the antilog of the logarithm of any given function is just the given function, or the antilog of the logarithm of x will just be simply x. And this should be equal to 10 raised to 2.301, and x now will be equal to 200. This is the value of x without the logarithm sign, because the problem is just asking for the value of x, it's not the log of x. So the answer will be x equal to 200. And if you try to check the validity of this one, try to get this value here, put it in the original equation, and what should come out should be a 4 is equal to 4. True. Right? Meaning to say the answer x equal to 200 will be equal to, or it is the correct answer. Okay, example number 2. It's an easy one, right? So as long as we follow the concepts of logarithms, okay, it's easy to solve logarithmic equations. Example number 2, it will be still a logarithmic equation, but there's a little bit variation. Okay, I will try to present the problem. The logarithm of x plus the natural logarithm. This is natural logarithm, this is common logarithm. Natural logarithm of the ratio x over 8. And this should be equal to 5. Find for the value of x. Okay, let's try to bring out the solution. We just copy log of x, and this should fall under the natural logarithm of equation. With their common logarithm or natural logarithm, okay, the resulting expansion will still be the same. So it will still be the natural logarithm of the numerator minus the natural logarithm of the denominator, and this should be equal to 5. Log of x, okay, we got a problem here because this is under natural logarithm sign and this is common logarithm sign. And to compute for x, okay, we must have to make the log here common to both. Okay, but there is a relation from our previous discussions that the natural logarithm of x is equal to 2.3 times the common logarithm of x. Okay? The relationship of this with respect to log of x is actually by the factor 2.3. So actually we could replace this one by this value here for it to be under common logarithm. So log of x, we replace this one by 2.3 log of x. We derived this one the last time around. The relationship of natural log and common log is actually by the factor of 2.3, and natural logarithm is actually larger than the common log. So this is 2.3 common log of x, and this should be equal to 5 plus. We transpose this to the right, plus the natural logarithm of x. Okay? This is 1 logarithm of x plus 2.3 logarithm of x. They are common, right? The coefficient here is 1, this is 2.3, so if we try to take the sum combined, that will be 3.3 under 1 log of x, and this should be equal to 5. Natural log of 8, use our calculator, 2.079. So log of x now will be equal to 7.079. There is a 3.3 over here, so we will multiply this one by 1 over 3.3. Right? So it will now just simply log of x equal to 7.079 over 3.3. Log of x will be 2.145. Okay? This is now the resulting equation after the simplification, but this is not the value of x. This is log of x. So to compute for x without the log sign, we must have to eliminate the log sign. And we must have to take the antilog. The antilog of the logarithm of any given function is just the given function. And the proper way on how to compute for the antilog is that you get the base, raise that to the given left and right hand side. So it will be 10 raised to the logarithm of x, meaning we are taking the antilog of logarithm of x. And this should be equal to 10 raised to 2.145. But this one here, okay, is just simply x. The antilog of the logarithm of any given function is just the given function. So x now will be 10 raised to 2.145. 10 squared is actually 100, right? There is a decimal 1.145, so our answer should be greater than 100. X now will be 139.68. Okay, that's it guys. If you want to check the validity, put this x here, then try to simplify this one. What will come out supposed to be is 5 is equal to 5. Okay? If we try to put this as 139.68, and so with this one, we simplify, the sum should be 5 on the left hand side, and this should be equal to 5, meaning our answer is correct, so it is true. Okay, that's it guys. These are just example problems of logarithmic equations. It is included under the study of logarithms, under the study of trigonometry. The next time around, I might be discussing obtuse angles, okay? It's still a part of trigonometry, but this will be the last part of the study of logarithms, trigonometry lesson number 19, logarithmic equations. Okay, good evening from Los Angeles. Professor David Jettersway.